Going to cover sections 1, 2, and 3. So mostly terminology, so vocab words, and a little bit of math. So the title of our chapter is Thermochemistry, which is defined as the relationship between chemistry and energy. So there's a couple examples on here involving heat and light. These are the ones that we're most familiar with on our day-to-day lives, and it's also the ones that we deal with the most in class. So in the first one, hand warmers, the heat is released by the hand warmers, and with instant ice packs, the kind where you have to pop the inside, the heat is absorbed, so it feels cold to the touch. Another example are light sticks. When we crack them, we allow the chemical reaction to occur, and it releases light. So all of these are example of energy, either in the form of heat or light. So a couple new words here. Energy. Energy is defined as the capacity to do work, and work is defined as a force acting through a distance. So this can be pushing against something. So think about pushing a box up a hill, so you're fighting gravity. That's the force you're acting against. In chemistry, the force that we're acting against is often the chemical bonds. In order for new bonds to form, old bonds have to break. Now, in addition to work, energy can also involve heat, which is a flow of energy. And so we'll talk a lot about heat in this chapter. That's the type of work that we tend to focus on, or type of energy we focus on. We break energy into two main categories, kinetic and potential. Kinetic energy is associated with motion, and potential energy is associated with position. A couple examples of kinetic: thermal energy. Might not sound like there's motion involved there, but things get warm because the molecules are moving around more. Mechanical is literally you moving your arms, or a piece of equipment moving so that your car can run. Electrical, that's the movement of electrons, and sound, it's the movement of sound waves. Potential energy has to do with position. Gravitational is usually the most common. We talk about this in terms of swinging a baseball bat or a golf club. It has a lot of potential energy when you're at the top of your swing. The guy at the top of the diving board has potential energy. Chemical energy fits into this category, and this is the energy that's stored within an atom based on the attractions between those subatomic particles. And then electrostatic is, again, the attraction between a positive and a negative. So this is a very general term, but there's energy stored within that attraction. So if we break that attraction, we had the law of conservation of mass in earlier chapters. We now have the law of conservation of energy. This is also called the first law of thermodynamics, and it states that energy cannot be created or destroyed. So all of the energy we have in the entire universe is constant. We're not getting any extra, and we're not losing any, which sounds really weird. How we deal with that is that energy can be converted. So that chemical energy that's in the food you eat, your body converts it so that you can use it as mechanical energy to move around. And thermal energy from the sun is converted into chemical energy so that plants can grow. So there's a lot of changing of types, but we can't change how much there is. Two other important words, system and surroundings. Now, we don't use these a whole lot in this chapter, but they do come up a lot in Chem 1B, and they'll come up a lot when you take physics. The system is whatever we care about, so generally it's our reaction. The surroundings is everything else, so the beaker itself, your hands, the counter, the people around you. We have to take those into account, because if you're holding onto your beaker, you could be warming that beaker up. Now, one of the things that can be confusing, especially if you're taking physics right now, or if you take physics at the same time you take Chem 1B, is the way that we define system and surroundings is the opposite from physics. Physics cares about the surroundings, and we care about the system. So if equations look different in physics, even though they're talking about the same thing, that's probably why. On to the math. So when we measure energy, here's our equation. Kinetic energy is 1/2 mass times the velocity squared. Now, we don't actually use this equation. We just have it on here to look at the units. So the SI unit, or the standard unit that we use, is a joule, and 1 joule is defined as a kilogram times a meter squared times a second squared. These units look super weird, but they're coming from this. So the mass is in kilograms, the velocity is in meters per second, and we're squaring it. So joule is a very common unit. The other one is a calorie. Now there's 2 calories on here. Calorie with a lowercase c, calorie with a capital C. A lowercase calorie is defined as the amount of heat that it takes to raise the temperature of 1 gram of water 1 degree Celsius. So a very specific definition. Now, we also have calories with a capital C. It takes 1,000 lowercase calories to make 1 capital calorie. The only reason this unit exists is so that when we make our nutrition labels, it has a nicer number on it. So the candy bar that you ate that was 200 calories is really 200,000 lowercase calories. Now in other countries, they don't use this system. So this is, I think I stole this from Australia, but on their can of soda here, the nutritional information is listed in kilojoules and kilocalories. So 1 capital calorie is the same thing as a kilocalorie with a lowercase. They're used to the metric system though, so a kilo makes sense to them. So here's our conversion factors here. A couple practices with this, and I got the rest of the conversion factors from table 6.1 in your book. So the first one is 534 kilowatt hours to joules. And we're going to make sure we're checking our significant figures and our units as we go through this. So here's my starting point. This is my conversion factor, which is directly from that table in the book. And we get 1.92 times 10 to the 9th joules. And again, 3 sig figs, so 3 for the answer. 215 kilojoules to capital calories. 215 kilojoules, we convert that into joules, and then our joules can be converted into calories. Now you have to be careful when you're writing down calories. Definitely emphasize a big C or emphasize that little c. If on your paper it looks like it's somewhere in between, you might confuse yourself, or you might lose points on a test. We do the math, we get 5.14 times 10 to the 4th capital calories. 567 capital calories into joules. We just need that 1 conversion factor, and we get 2.37 times 10 to the 6th joules. And last, for joules to little calories, notice our conversion factor for these two is almost the same. It's just a difference of where that decimal point is, so a difference by 1,000. 6.81 times 10 to the 4th calories. So these conversion factors are not any different than what we've done in the past, just the numbers themselves are different. Now I mentioned the first law of thermodynamics is the same thing as the law of conservation of energy. And the other thing on this slide is telling us that a state function is a function that only depends on the end state and the starting state. It does not depend on the pathway. So an example down here are these people climbing. Everybody started out at an altitude of 0 feet and ended at an altitude of 10,000 feet. So their change in altitude is 10,000 feet. That's a state function because it doesn't matter which pathway they took. Now if we want to know the distance that they hiked, the people on the steep path over here traveled 5 miles, and the people on the zigzaggy path traveled 12 miles. The pathway does matter. State functions, altitude, path does not matter. Something like your driving distance or your hiking distance, the pathway does matter, and it changes that overall number. A couple more terms that we're going to look at on the next 2 slides. This one is specifically looking at an exothermic reaction. So here's our reaction. Carbon and oxygen combine to make CO2. This is an energy diagram. We're going to see these throughout the semester, and you'll definitely see them a lot in Chem 1B. This is the energy of where our reactants start. So they're starting at a higher energy level than where they're going to end up. So here's our products down here. This arrow is representing the change in energy. So it tells us that the energy is decreasing as the reaction occurs. So for the system, for our reaction, the energy has gone down, so it's a negative number. Now, negatives and positives in chemistry don't really mean the same thing as they do in a math class. They tell us the direction that something moves. So this is a negative number because that's telling us how much energy our reactants have lost. The energy has to go somewhere because of the conservation of energy. It can't just disappear. So that energy flows into the surroundings. It warms up the air, it warms up the beaker, it warms up the counter. And so the change in energy for the surroundings is greater than 0. It's positive. These two numbers are the same thing, just opposite signs. The system loses the energy and the surroundings gain the energy in the same amount. Now if we take that same reaction and flip it around, now our reactant is lower in energy than our products. So to go from the reactants to the products, we have to add energy in. We have to increase energy. So our system is gaining energy. So our change in energy is going to be a positive number. And the energy has to come from somewhere. So the surroundings are losing energy. And so the delta E for the surroundings is going to be negative. And again, those two numbers are the same thing, just an opposite sign. And when this occurs, we say that the reaction is endothermic. So the way that I remember this is that exothermic is when the system has heat that is exiting. So exothermic energy is exiting. Endothermic is when the heat is going into, or into. And so a little play on words there might help you remember. This slide is connecting work and heat. So when we look at the total energy of a system, it's incorporating the amount of work that is done and the amount of, oh, I did that backwards, I'm sorry. The total energy is the amount of work plus the amount of heat. So we can incorporate both of those processes together into one equation. And then lastly, I've used the word heat a lot, and we obviously know what it is, especially living in Fresno, and especially after this Labor Day weekend. But there is a difference between heat and temperature. Heat is the exchange of thermal energy. So you go outside and you get hot because the air around you is hot. You go inside with nice air conditioning and you cool down because the air around you is cool. Either the heat is going into you or the heat is leaving you, but there's an exchange of energy. Temperature is a measure of that energy. Thermal equilibrium is an idea that we're going to use when we do the math in here. If you have two objects that you put together, if they're at different temperatures, they're going to continue to have an exchange of energy until they reach the same temperature. So for example, if you put ice in your glass of water, the water is going to cool down and the ice is going to warm up until they reach the same temperature. Alright, that is it for this video. Thank you.